When the pH is 7, then it's a case where the sample is neither acid nor base. But less than 7, it's an acid, we say. More than 7, it's a base all the way.
Imagine your whole class went on a field trip for school, and they visited a hydrochloric acid plant where they produce hydrochloric acid. Now they all went, but you stayed at home for whatever reason. You might have felt sick on a day, or you just bludged, but you were at home and they went to that field trip. Now all of a sudden you get a call, so you're at home and you get a call, and your classmates are telling you that there's been a huge trouble, there's been an explosion at the power plant or the production facility, and they're asking you to help them rescue them. So in that case you might think, okay, well it might be smart for me just to go there and just save the day. So once you arrive, you find a sign saying danger acid. Obviously now it might hit you, you're at a hydrochloric acid power plant or production facility, and you're dealing with acids which might be quite dangerous. Now, hydrochloric acid is a very strong acid, and if it has a 0.1 molar solution concentration, that means it's going to have a pH of 1, so you might be scared of actually getting in contact with that acid. So what could you do to decide if it's safe or not? So you want to go in, but you might not want to be burned by a pH of 1.0. So in that case, what you could do is you could actually grab some of that sample, so grab the hydrochloric acid sample, collect it in maybe in like a bucket, have your sample, and then head back to school and do your titration. Right? So you can do a titration to figure out the actual concentration of that unknown hydrochloric acid. And if you figure out the concentration, you can also figure out the pH. And then you can figure out if it's actually safe for you to actually go in there and rescue your friends, or if it's better for them to die because it might be too dangerous to go in. So in that case, what you could do is you could first figure out your known solution. You've got a base at school, you know the base, it might be sodium hydroxide or anything else, it might be a strong base, and you know the actual solution of it, the concentration, which is 0.1 mole per liter, and let's say we have 1 liter of that solution. Through the concentration equation, which is this one here, you can figure out how much moles there is in that solution. So we've got 0.1 is our concentration, N is what we want to try and find out, how many moles there are in, and V is our volume, and that's 1 liter, so that's 1. So we bring up 1 to the other side, we have 0.1 times 1 equals N. So now N is 0.1 times 1, which means that is 0.1, which means in that solution we have 0.1 moles of our base. And remember, this is a neutralization reaction we're going to do. Titration is basically a neutralization reaction. In a neutralization reaction, if we have, especially if there's strong acids and strong bases, if we have equal amounts of acids and bases in terms of its mole numbers, that will balance each other out, and we'll be left with water and salt, so at a pH of 7. So once we've equaled them out, equal amounts of moles of acids and bases, we're going to be left with a pH of 7. So now that you've figured out how many moles of that in our base there were, what you can do now is you can grab that sample of hydrochloric acid that you got from the factory and test it against the base. You want to see how much volume it takes for there to be equal amounts of moles. Right? So what you can do is you can do a titration, and let's say it took 2 liters to actually do that. It took 2 liters instead of 1 liter. So now what you know is if it's neutralization, so if neutralization happened, that must mean that base and acid must be equal. So that must mean we also have 0.1 moles of the actual acid. So in that case, in this same equation, we have concentration, which is what we want. We don't know the concentration, that's the unknown of the acid. So we want to figure out. We know our moles must be equal to the base moles, 0.1. And we know that our concentration, that our volume was 2 in this case. So if we do that, put that in a calculator, 0.1 divided by 2, what we get is 0.05, and what that means, that has a pH of 1.5. Now after figuring out the pH of this actual solution, that the acids in that factory has a pH of 1.5, you might decide this is a bit too dangerous, you don't want to go in there and get burned by a really acidic pH, and that means you might call back your friends and say, you know what, I can't go in there, it's too dangerous, sorry guys, you're on your own, right? But you did that after you found out what the pH was, and you did that using titration. And that's what we're going to discuss in this video. First, in this video, we're just going to talk about how we actually prepare a standard solution and how we can conduct a titration. And this is what the dot point says. Describe the correct techniques for conducting titrations and preparations of a standard solution. Those two things will be what we're doing. And next video we're going to cover more of the theory behind it as well. Let's start with talking about the correct technique for conducting titrations. Let's describe the correct technique for conducting titrations. Now again, remember with titrations, the point of doing titrations is to find the concentration of our unknown acid or base. So whatever we're checking is the unknown, is our acid or base. It's called our titrates. That's actually something you should remember. Our titrate is the word for the thing that we don't know the concentration of, the thing that we're checking. And there's also another word called the aliquote. I have no idea how to say that. But the aliquote is the thing that we know our concentration of. Right? So in our example, we said that our hydrochloric acid was the one we want to figure out. That's our titrate. And the aliquote would be the base, which in this case would have been like something like sodium hydroxide. And the idea behind titrations was to find the concentration of the unknown, so find the concentration of the titrate. And to do that, we need to be able to find first the number of moles there is in our actual titrate. So what we should do is first we have the burette, which contains our concentration of unknown concentration of the acid or base. In our case, hydrochloric acid in our example. And again, this was the titrate. So that goes into our burette, and the burette is this thing here. It's just a long tube, we can quite easily measure it. It's quite detailed, and has a stopcock, which means we can open and close it. And in this case, in our example, we had the hydrochloric acid in here. But yeah, unknown solutions, we didn't know what the concentration was. We just knew that it was hydrochloric acid. Now, the reason what we have to, before we actually put the acid inside, is we have to wash it. Remember, there might be dirty or whatever else, so we have to wash it. But we can't wash it with water, because if we wash it with water, we might dilute the actual concentrations. That would give us a false result. So in this case, we have to actually wash it with the same acid. So we wash it with the titrate. So before we put the titrate in and measure it quite accurately, we actually use the same titrate to wash it, to make sure that there's nothing that disturbs, there's no base left over from previous titrations. It's all pure. So we wash it with the titrate first, then it's clean, and then we put the titrate in again until a certain point. Now the second one, the flask contains known concentration of acid or base, and that was our aliquote. And in this case, we said there might have been a strong base, such as sodium hydroxide or something else in our aliquote. And the third step is we have to add an appropriate indicator, and we add the appropriate indicator into our aliquote. So in here. Now it says appropriate, and I'm going to go over more of why it needs to be appropriate in the next video. The basic idea is that we're trying to get, so we said earlier, this example here, we're trying to get to a point where all of the bases, the acids and bases are completely reacted together. They have been converted into salt and water. And for example, if it's strong acid and strong base, that conversion will happen at a pH of 7. So we have to have some way of figuring out what the actual pH is. And we can do that by using indicators, and by using the appropriate indicator. So for example, using phenolphthalein is an indicator which only tells us if there's a change in color at a pH of about 9 or 10 or 8 or so. Whereas if you use bromophenol blue, that tells us if there's a change in pH at around about a pH of 7, which is what we actually want. So we're going to use bromophenol blue as an indicator if we're using a strong acid and strong base titration. But we're going to talk about more in the next video. So now that we've done that, we have our acid in the titrate as our titrate, we have our base as our aliquote. What we do next is we open that stopcock, which is the thing that we can screw open and closed, and we're going to add bits and bits of the acid, bit at a time. So our titrate will go into the flask, bit and bit at a time. And the point of that is we're trying to neutralize. We're trying to get to that point where the color changes, which means that neutralization has happened to the fullest degree, and the acid and base have completely neutralized. So we're going to open it bit at a time, and we're going to open, and we're going to do that until we find the end point. And the end point is when the acid and the base, there are equal amounts of acid and base in there, and that means it was neutralized. That's our end point. So for example, if we know there were, let's say, 0.1 moles of a base in there, and we've had that color change, it changed to green, that means there must also be 0.1 moles of acid in there at that time. So once that happens, we know there's equal amounts of acids and base concentrations in there, especially if they're, in this case, if they're all both strong acids. Right, so that's what we do, and this is the same procedure quickly, but there's a couple of things you should also often do when it comes to titrations. First of all, you might actually put a white paper under the flask, and I'm going to go over in a second why it is, but that can be quite important as well. And you might make two solutions. One solution which is considered your control, and the other solution is the important solution. In this case, you have your white paper under the flask, and then what you're going to do is you're going to have your indicator in this flask, which is under the actual titrate, and you're going to add your titrate in bit by bit, and eventually you're going to come to a point where it's going to be a sudden change in color, and that's the end point. That's what you're looking at. So all of a sudden, the color has changed. Now you reach your end point. And the reason why we use, for example, this white paper is that so you can clearly see the color change. It's a bit hard to see it changing really rapidly if there's no white paper under it. And the reason why we have two solutions is because now you can check the original solution. So this was how it looked like originally with the endpoint solution. And you need to do that because you need to get that fine point exactly where the color changes. And by having a comparison, it's easier for you to identify, has the color changed or not? Has it actually changed? And what you should also do, the closer you get to your endpoint, the more you should swirl the actual flask. The reason why you swirl is because then you're actually shaking the solution, you're mixing the solution better, which means you get a more accurate result. So make sure to always swirl as well, especially when you get close to the endpoint. And once you've done that, so once you've figured out the endpoint, doing a titration, that's going to be something called the rough endpoint. The first time it's going to be a rough endpoint because you're going to have maybe let in 5 mils at a time. It's going to be pretty exact by the time, so let's say 5 mils, then suddenly you get to the endpoint and the color changed. But you could still do it more exact. You could still add only 1 mil at a time. So the first time is going to be quite rough, but then you're going to know roughly where the actual endpoint is, which means the second time, when you get close to the endpoint, you only, instead of doing 5 mils at a time, you might only do 1 mil at a time when you're close. That means the result is going to be a bit more accurate. You're going to get closer to that change, which is the one you need to note down. Right? So that's your titration techniques. Remember that to rinse your burette with the actual titrate, so whatever the titrate was is what you should also rinse your burette with. Remember to put in the appropriate indicator, which you have to figure out yourself, depending on if you're using a strong acid and strong base or what else you might be doing. Remember to put your aliquate, so your whatever your base or acid is that is known, into your flask, and then just do titration. Figure out that endpoint. Do a couple of tries to get that exact endpoint, or as exact as you can do it. And that was a titration technique, but we still have to figure out how we actually. So it says we need to have a flask which contains known concentrations of acid or bases. We still have to do that. We still have to make a known concentration of acid or bases, and that's often called our standard solution. And that's what we're going to do now. We're going to do a standard solution. How to do that? So it says preparing of a standard solution. So first you have to select an appropriate base or acid to use as your aliquate. Remember, on aliquate we need to know exactly what the concentration is. For this we need to know exactly what the concentration is for it to be a good aliquate. Now, we might think, okay, hydrochloric acid or potassium hydroxide, sodium hydroxide, or sulfuric acid. These acid bases are ones we often use when it comes to experiments in your lab. You might think, oh, well, they might be pretty good to use. But the problem is, especially because we have to weigh them, so we'll make them ourselves. So you're going to weigh the dry mass first, and then you're going to add the dry mass to water and make a solution. Right? So you're going to do it from scratch, so you can figure out exactly what the concentration is. But the problem is when it comes to weighing hydrochloric acid or potassium hydroxide, or the other ones, is if you actually put it on a scale, the dry mass, and I've realized the mass itself, I don't know why I chose the color brown. I'll choose a different color because it looks a bit weird. I'll choose yellow. Looked like a turd. But yeah, the idea was if you have these other ones, right, sometimes you actually have water being absorbed by the mass, which means the actual dry mass will be higher than it should be because the water will add to the waste. Or other ones, you might have carbon dioxide leaving once you put it on outside, once you try to actually measure it. And if you have carbon dioxide leaving, that means it's going to be lighter than it should be. So these examples, hydrochloric acid, potassium hydroxide, etc., they're all bad examples to use because they're not really that accurate. Because they're going to have a mass which is not perfect. Instead of using these, the appropriate ones we should use are, for example, sodium carbonate for our base. So sodium carbonate is a good base to use. A standard base. It's quite accurate. And the formula is Na2CO3. And a good acid to use would be, for example, benzoic acid. Benzoic acid. And that would be C7H5O2. And these are examples where this doesn't happen. Whereas when we weigh it, we get the accurate result, right? So once we've weighed it, right, so we have the dry mass of the selected base or acid, and we weigh it. That's the second step. After selecting the appropriate one, what we do then is we take that dry mass and put it in a beaker. And then once we put it in a beaker, we add some water as well. That's the third step. Put the dry mass in the beaker and add some water and stir. Right? It should dissolve. So eventually you're just going to see that kind of solution. It's not going to be having any chunks in it. It's going to be dissolved. And this happens because you're stirring. So now we have a solution. But we still have to move it into a flask. Right? The flask will have our base or our acid or whatever our aliquot is. And we have to still put it in. So we're going to use a pipette to actually transfer it from the beaker into the flask. And the pipette itself should actually be washed with, so it should be washed with whatever the aliquot is. So for example, let's say we have sodium carbonate, a certain solution of sodium carbonate, we made that up. We'll wash the pipette beforehand, we should always wash our stuff. We'll wash it with the same sodium carbonate solution. And the reason why, again, if we use water, for example, we could dilute the solution, and that means we have an unknown solution again. So make sure the pipette, you're gonna wash with your same aliquot solution as you have inside. So wash it out and then put it up to full, however much you need, and then put it in there. So now let's say, okay, the stuff in the beaker we transferred into the flask, and that makes up so much of our solution. But you can see here we have actually much more. It's full, whereas here it's not full yet. And the reason why is because we know this whole solution might be really concentrated. Let's say it's 1 mole per liter. So it's a bit too concentrated. We don't want to have that concentrated. But we know this is 1 mole per liter. So if we add a certain amount of water, and we'll just fill it up with water. If we add a certain amount of water now, that means we can get it from 0.1 mole to, from 1 mole to 0.1 mole per liter. And that's what we want, right? So here we know this here is 1 mole per liter. Now by adding a certain amount of water, we have to be quite exact. Then we can bring it up to full. Whoa, that was not what I wanted. Yeah, I just want to make it full. But obviously that won't work. But the idea is that here we actually increased water content just to bring it to the full. And that's how we got our sample solution of aliquot. So I'll quickly go over the steps again. For titration, we should make sure our burette is washed with whatever our titrate is before we put in our titrate. Then we put in our titrate. We have our flask, which has our aliquot, which is the known concentrations of acid or base, depending on what we're using. Then we need to use an appropriate indicator, so we can figure out what the actual endpoint is. Then we'll add bits by bits. That's step 4. Open stopcock and add bit by bit. We're going to do that until we reach the endpoint. That's when the color changes. The first one will be the rough endpoint because we have been quite unexact. But then we're going to do it a couple times to be more exact. And then we're going to take the average of those, which will be our endpoint. That was the titration. And how do we get this solution of flask? This original solution. That was to prepare a standard solution. We need to select first the appropriate base or acid. For example, for the appropriate base would be sodium carbonate, NaCO3. Appropriate acid would be benzoic acid. The reason why is because when we weigh them, they don't add mass or lose mass to the atmosphere. They stay exact. we'll often dry them as well, so we could actually might put them into an oven just to be sure that there's nothing but that thing in there. Then we wait once we've done all that. Once we've weighed it, we put it in a beaker and we add some water to dissolve it. Then we transfer that from the beaker into a flask. The parts of it will be the actual solution. It might be really concentrated, so we add some more water to a certain point. And then we have a known concentration. We have a known concentration of our aliquot. And then with that, we'll use that for our titration. But yeah, I hope that was useful.
Thank you for watching.